We previously saw how to do a linear approximation of a function near a given point using the tangent line of the function at that point. So in particular, the linear approximation, which we call t1 of x, this is just the equation for the tangent line, is equal to f of a plus f prime of a times x minus a. So this is exactly the equation for the tangent line to f of x at x is equal to a. And this makes sense for the following reason. So let's say we have some function like this, and we have some, this looks like a good point, and then the tangent line something like that. Okay, so when we have a line, right, we start off with an initial y value, which is just equal to f of a. So at the point x is equal to a, the output should be f of a, the same as it is for the function. So we're going to start off with f of a, and then as we move forward along, and if we follow the tangent line, we're going to have a delta x. So if this is the value of x, delta x is just going to be x minus a. So this length is x minus a, and this is the delta y, the change in y, which should just equal the slope times delta x. So the slope is equal to the derivative and then times delta x, which is x minus a. So the reason this works is that this is basically y0 plus a slope times delta x. So there's the slope, there's the delta x. It's just your starting y value plus the delta y. So y is equal to the initial y plus delta y. And delta y is given by the slope of the function times the delta x. So this is the tangent line. And we'll note that there's a few properties, two properties in fact, that we should note. So first of all, the tangent line evaluated at a is equal to f of a. You can see this because if we plug in a for x, we get t1 of a is f of a plus f prime of a times a minus a. A minus a is 0, so it's just equal to f of a. But also, t1 prime of a is equal to f prime of a. We can see this because the derivative t1 prime of x, well, the derivative of f of a is 0. Derivative of x minus a is 1. So we just get f prime of a. So the derivative of the tangent line is a constant. It's just equal to the derivative of the function at that single point x is equal to a. So you can think of the tangent line, or also known as the linear approximation to the graph at the point a, or the linear approximation to the function f at the point a, as the unique linear function that passes through, it has the same output value at the point a as the function f does, and it has the same derivative at the point a as f does. So it's just the unique linear function that satisfies these two properties. So you might say, well, what if I want a better approximation to this function near this point? So instead of using a linear function, what about using a quadratic function? So that's the topic of our lecture today, and that is quadratic approximations of functions near a point. So to see this, let's set up a general quadratic function. And since everything's centered at a, I'm going to call it t2 of x. I'm going to say it's equal to capital A plus capital B times x minus a plus capital C x minus a quantity squared. Right, so this is a general quadratic function, and instead of using just x and x squared, I'm making my life easy by using x minus a. Right, so it's still a quadratic function because if you expand, you get bx minus little a times capital B. And then here you get x squared minus 2ax plus a squared, but again, it's still a quadratic function. And so instead of just setting it up as capital A plus capital BX squared plus capital C, or capital BX plus capital CX squared, I'm setting up, instead of using x, x minus a. So let's find the coefficients capital A, B, and C such that T2 of A is equal to f of A, T2 prime of A is equal to f prime of A, and T2 double prime of A is equal to f double prime of A. So let's just add one more condition. So the second derivative of this quadratic function should also equal the second derivative of the function f when evaluated at that point. So in other words, this is the single quadratic function that best approximates the function f. And we know in the sense that it shares the value of f at the point A, it shares the derivative of f at the point A, and it shares the second derivative of f at the point A. So in terms of all quadratic functions, this comes closest to approximating the function f. So first one, well, T2 of A, if I plug in little a for x, a minus a is 0, a minus a is 0, T2 at A is just equal to capital A. So therefore capital A should just equal to little f of x. So let's rewrite T2 of x as f of A plus b times x minus a plus c times x minus a squared. Now to get to T2 prime of A, we're going to first need T2 prime of x. Well, the derivative of f of A is 0 because f of A is just a constant. Derivative of x minus a, this is, you can think of this as a chain rule or a power down rule. It's x minus a to the 1. The 1 comes down, x minus a to the 0, which is 1. So we get b plus, here we have x minus a squared. The 2 comes down, 2c, x minus a to the 1. The derivative of the inside is 1, so it's just 2c x minus a. And then similarly, T2 double prime of x, derivative of b is 0, the derivative of 2c times the quantity x minus a is just 2c. So those are the derivatives of T2 and the second derivative of T2 anywhere. Now let's look at T2 prime evaluated at the point A and T2 double prime evaluated at the point A. So T2 prime of A is just going to equal b, because a minus a is 0. So when we evaluate this at the point A, we just get b. And T2 double prime of A, well, that's just equal to 2c, because T2 double prime is in fact a constant. So in order to match this up with f prime of A and f double prime of A, we want to set the coefficient b to equal f prime, and then of course the coefficient c has to equal f double prime of A over 2. So the result is that T2 double prime of x is going to equal f of A plus f prime of A times x minus a plus f double prime of A divided by 2 times x minus a squared. So this is what you can call it the tangent quadratic, or the quadratic approximation. Quadratic approximation to the function f at the point x is equal to a. So in this example, let's compute the quadratic approximation. Compute the quadratic approximation for f of x is equal to sine of x at x is equal to, let's do pi over 4, why not? Pi over 2 is good. Let's do pi over 2. Right, so sine of x looks like this. And here's pi over 2. So we would expect this as a quadratic, so we would expect something that some sort of quadratic that is pretty close to the sine function like that. Okay, so we need so here a is going to be pi over 2. So f of x is sine of x. We need f prime, and f double prime. F prime of x, derivative of sine, is cosine of x. And f double prime of x, derivative of cosine, is negative sine of x. So now let's evaluate these at pi over 2. So f of pi over 2, sine of pi over 2 is 1. F prime, let's do it anyway, of pi over 2 is 0. And f double prime of pi over 2 is negative 1. Right, because cosine of pi over 2 is 0, sine of pi over 2 is 1 again, but then we have negative sine of x, so it's negative 1. So therefore, the quadratic approximation, T2, in your notes, scratch out the double prime. It should just be T2 of x is all of this, not T2 double prime. T2, what happened here? T2 of x for the sine function at the point pi over 2. So f of pi over 2 is just 1, so we get 1. F prime was 0, so we skip this term. F double prime is minus 1, so we get 1 minus 1/2 x minus pi over 2 squared. So 1 minus 1/2 x minus pi over 2 squared. So what we can do is we can plot this. So plot sine of x, and then 1 minus 1/2 x minus pi over 2 squared. Let's go x equals minus 0 to pi. Minus 1 to 4. Minus pi to pi. Okay, so here we see the sine function. Let's make the width a little bit larger. So the sine function we'll make in blue, and then this function 1 minus 1/2 x minus pi over 2 squared is in red. So we can see that it does, so here's the sine function, and then there's the best quadratic approximation to sine of x near pi over 2. So you can see that it does a good job of approximating sine of x pretty much between pi over 4 and 3 pi over 4. It's very close to sine of x. Now the linear approximation, you'll notice that f prime was 0, so it's just a horizontal line. So notice that the horizontal line, let's add that one in there. So the horizontal line is the tangent approximation, which it approximates a function, but only very, very close to pi over 2. The quadratic approximation stays close to the function for a much, much wider range of values. So you get a more accurate approximation that's valid on a larger region. So that is what the quadratic approximation for sine of x looks like near the point pi over 2.